We're moving straight into our second speech, and I want to introduce Keith Hogan, who is the CTO of PixSpan. He will be talking about some image corruption in the workflow and how to stop this from happening. So please, Keith.
So kind of a little switch from what Floyd was talking about, which is kind of a big umbrella topic, to kind of dialing down into the details. Nice clicker here. Diving down into details of a very specific problem. Tried to look at the topic of image corruption in the context from onset all the way to archive. Turns out, most of the issues are exactly the same, throughout that scenario. And also, in looking at problems, it's easy to sort of see sky as falling type of thing and think that how does anything work? But that's not the case, but try to also provide some solutions to that, some proposals. And, it can be dangerous to mention proposals in front of a standards committee. So let's take a real deep dive into the file format of an image. What you see here on the right-hand side is the file format of a DPX file. Now, a DPX file is one of the more simply constructed file formats. Other formats like TIFF and EXR are very more complex. But so what is corruption? Corruption, one might think when they're talking about an image file, the corruption of the raster data itself. But there's lots of other opportunity for corruption, and there's some key things in a file format that, if corrupted, can really cause a lot of problems. There's complex metadata, there's pointers, internal pointers, that if they point to the wrong place are going to mess up. Most people really don't ever deal in these details, so if corruption happens in those areas, there's really not much that they can do about it. It's something that they find and they notice, but can't really fix. And then the other complicating factor is if somebody does know what a file format looks like and can look into it, a lot of the file formats aren't standard, so that can get confusing. This right here is an example of a corrupted image file. And if you happen to have a color scientist sitting next to you, they can lean over and tell you exactly which of the one particular bits is flipped in that image that created this corrupted file on the right-hand side. Most people are going to look at it and go, oh my God, that file is really screwed up. Others are going to wonder why, a picture of the Shroud of Turin is showing in the middle of their clip. But this is just one bit, and this can show you how easily, a very simple corruption can cause a problem. Nobody's curious about what bit that is. So how do we catch bits like that? The bits are caught by a common practice in the industry, which is to take hashes at basically every single stage of the workflow. When you move it from archive to nearline, you take a hash. When you move it from nearline to online, you take a hash. So, and back, all around the workflow, put it on tape, you take a hash. So what happens when the hash doesn't match? Well, you're typically loading the file, restoring it for some backup copy. But there are problems with doing that, and the biggest problem is that nobody has idle resources sitting around waiting to jump in and solve these problems. So your LTO is busy, and you put a ticket in, and you're going to get that file restored at some point in time. So a master MD5 file is kept, and you can compare your MD5s against that. But this hashing is really inefficient, and it's inefficient because the hashes don't really quantify the errors. They just tell you that an error happened. And just as an example, here's another 1-bit change in a file, and you can see on the screen that there are the two MD5 hashes for those frames, one with a corrupted bit and one is the original. Now that's a good thing, because that's what the hashes are there for. They're there to detect these errors, as small as they may be, and let you know that there's a problem. But again, it doesn't give you any sort of indication of whether it's fixable or not. The hashes also don't locate where the error is, so the error could be in any part of that image. It could be in the metadata. It could be in a letterbox area, totally black. It could be in some inconsequential place of the image where if you look at the cost of restoring it versus it's going to an artist anyhow and it's in the bottom left-hand corner, they could just fix that. You know, that would be a consideration that if you could locate where the errors were, that would help out. One thing about errors in the metadata is that it's possible to fix those and fix it in a way that you go back to a matching MD5. So how can you really improve this situation? Well, so we're getting to a time where you know, Moore's law has given us lots of processing power. And a lot of things in the workflow use that processing power, but a lot of times machines are sitting around with idle processing. So what can you put that to? Well, you can put it to creating format-aware tools. So if a shop does, I bet you there are a lot of shops that primarily deal with DPX. They deal with DPX all day long. It's the same format. It's 10-bit, it's RGB, whatever. The ability to take a very short period of time, create automated tools that actually go look at file sequences and say, well, you know, I see that I have a problem. Is that problem in the metadata? Can it be fixable without having to go to a backup tape? And then maybe can it be automated in your system so a human never touches it, it just automatically gets fixed. And we've heard a lot about you know, different mechanisms with machine learning and things like that. You know, these things are very easy to do, very easy to put together. You know, one sort of thing you may look at is, hey, in a 4K frame, the metadata is, I think accurately, it's 0.00004% of the size of a 4K frame. So it's very tiny. That being said, there are vulnerabilities in the workflow that actually see where the metadata is more vulnerable than maybe the raster data is. So one very, very straightforward thing is instead of doing an MD5 or a hash on the whole image or the whole file, you can do the actual raster portion in various segments. This is just an example. Well, you could do letterboxes with one, you could do sides and tops and bottoms of the image with another, and the main focus area with another. And if you had an error in an inconsequential place, again, you can fix it. You know, it doesn't have to be in these big chunks now. Again, Moore's law, we've got tons of processing power, we've got GPUs. You can make your sections very, very small and have 10,000 sections or 1,000 sections. And that way, again, it's sort of a business decision. Do I go to that backup tape? Do I take that extra day? Do I delay this particular task? Or do I you know, bite the bullet because I know it's in an inconsequential place in the format? So this is looking from the workflow, going from onset to archive. You basically go through the same kind of computer equipment. You go through workstations, you go through switches, you go through storage. And all of these present a very similar type of situation. You're dealing with serial reliability from one component to the next component to the next component. And the way you calculate it over the whole system is basically you take a product of the reliabilities. From a practical point of view, what that means is you know, kind of the weakest link is the thing that's going to cause you the most problem. If you do have 10 things at the same reliability level, you will lose a nine, you know, a digit of nines. You'll lose to those 10 things in serial. But it's basically there are a lot of opportunities when you actually think about it. It's not storage and a switch and a workstation. It's several components going from PCIe buses to on-chip, layer 3 caches, all sorts of things. A good thing is that things have been built into the hardware to fix those, and and those have improved the reliability of this over the years. But at the same time, as the reliability is going up, the amount of data being shoved down the pipe is increasing exponentially. So again, it's kind of like fighting a losing battle. One good thing is that a lot of people have now said, gee, it'd be a good thing if we shared a lot of information about what's going on with our infrastructure and help the industry out, either the component manufacturers or the people who are using this equipment, help them identify where problems are being caused in their workflows and suggesting areas to fix it. So big studies at big compute centers, big providers like Google. Some of these are focusing specifically on SRAM and DRAM. Some are focused on hard drives. Others are focused on other workflow types of issues, but basically trying to discover where these problems are happening. If you go to the paper that's associated with the presentation, I have a lot of interesting links, one of which is a presentation done by Intel, and it's talking about how they improve their SSDs, the reliability of their SSDs. And one of the things that they do is they take it to Lawrence Livermore Labs and they stick it in front of a neutron beam, and then they try to discover where these problems are happening. And one of the things that they've done is they found areas where they can improve the situation, and that is by doing things like routing circuits in a different way. It's also by taking what may be two bytes that are next to each other and actually intermingling them so that the parity works better. So that if you get a hit of a neutron, a cosmic ray, it's not going to hit the whole thing, and it's going to catch that with their parity bit. So if you look at all of these studies that I looked at, and there were probably 10 or 12 studies that I looked at, they all sort of had common themes. And one of the main common themes, though there were some that said that this wasn't the case, but component failures were actually higher than they had expected, than they expected from the specifications that they saw for the components. And mainly issues were associated with the age of the components. So I know one thing that the industry does is it locks down a production and says, this is the workflow, this is the equipment that's being used for a production. But as that production is sitting there for 6 months or a year or whatever, the age of the components are going up, and that's potentially causing an issue. Certain obvious things like the level of heat, other issues associated with manufacturers, right? And this sort of goes to the higher quality manufacturer versus the lower quality manufacturer. So everybody's components may work the same, but maybe one component uses more lead or more ceramics. And lead and ceramics have been found to be sources of alpha particles, and alpha particles can go into your circuits and screw them up. So within the chip, the routing of signals within the chip. So, are you better off using a higher quality manufacturer? Probably yes. But for the most part, you aren't going to see the errors. But the problem is, do these infrequent errors cause you a lot of grief, either from a time standpoint or a cost standpoint? Altitude. If I were creating a data center, I'm not going to maybe locate it in Denver. Because it's going to experience more strange things that are going to be happening. And then this is an issue, it's not a problem, which is that manufacturers have incorporated things like ECC. So it's basically automatic parity, and you see that in lots of components. You see it in the caches that are inside of the processors, in addition to just your DRAM that you get. One good thing found is that the lower chip geometries don't look like they're causing problems. And in fact, when I looked at the problems across a lot of the studies, it wasn't actually that the bits were being changed within the actual DRAM cell itself. It's getting the information out of that through the circuits to get it out of the chip, or in some of the caching components. So, it's kind of like a medical situation where you go and, you read about some medical issues, and then all of a sudden you think that you might develop that disease because, you're familiar with it causes headaches and well, gee, I have a lot of headaches. So looking at all these things, I was like, well, gee, does my laptop really work? So as an engineer, as a software engineer, I have to be able to test out and see, how good is my laptop. So I wrote a little simple, stupid program. If you want to load it, you can load it and test if your laptop doesn't have ECC memory. Maybe you want to test it while you're flying across the United States. But I did that, and I was in a Southwest plane at 39,000 feet, ran it for hours, and sure enough, no errors. So I have faith in my laptop again. So not only is it hardware components that may be causing issues, it's also networking traffic, and networking includes both chips in routers and things like that, but also in software. And there's a study that was done, and it was done quite a while ago, but TCPIP really has not changed. That TCP is really, even though it's billed as a reliable protocol, it's really not very reliable. And it's not reliable because you can get corruption with some very simple things. And there's a list of things there, things like reordering of bits, and it doesn't cause an error. Now, TCP typically is going to run over Ethernet, and when it's running over Ethernet, there's a CRC, so that helps the reliability. But even running over an Ethernet CRC, errors can still happen in the workflow and cause bit errors. And again, you get the result of that with the Shroud of Turin, kind of look on your image. One thing that's very counterintuitive is that TCP is more vulnerable to full resolution images and also to big blank sections of metadata. And the reason is that you take two segments of TCP and you get a corruption, and somehow they magically get joined. And when you magically join those, guess what? The TCP checksum, which is a simple addition, one's complement addition, all of a sudden it passes the checksum. So this was found in empirical studies, and then the scientists looked into what was really causing the problem, and sure enough, there are vulnerabilities. So TCP is well known, Ethernet's well known, et cetera. There are other transport mechanisms that are being used all day long, things like WAN optimization, things like fiber channel. Fiber channel has lots of mileage on it and has good reliability, but some of these other transport mechanisms maybe haven't been studied as much as they could. And again, when you are at that point, maybe there's additional opportunity for error. And then other workflow considerations that are obvious, and this is something that people try to build into their workflow all day long. It's stop humans from getting involved, because when humans get involved, it introduces errors. So simple things like dropping of LTO cartridges or not storing them properly, or the sell-by date on the LTO tape was complete, except the tape got reused, and we know that the manufacturers of those tapes say don't use it past the sell-by date. So that is an issue. Other issues are software bugs, and it's not something you really think about, because when you test out a workflow and you lock it down for production, you've tested it with a set of test software that goes through it. But have you beat it up to the point so much that you identify all the possible software bugs? And the answer is no. Software is changing all the time. You get new versions, and even probably mid-lockdown, people sneak in some new versions. So software bugs include logic errors. It includes random writers that maybe happen once every year and a half, race conditions, timing, and then a big one is assumptions that memory's been initialized. So you assume that, and then you use it as if it's been initialized to some value, and it's not, and then all of a sudden weird things start creeping in. And then component manufacturing defects, certainly you get a bad run of disks and things like that. The good thing is if the disk fails right away. The bad thing is if it's sort of sneaking silent errors through your workflow. So there are some basic strategies to better improve this image integrity through your system. One of the things from the studies that I saw was that a lot of these errors were very transient, such that you get it to the other side, the MD5 fails, and you've got a problem. Well, okay, maybe don't go restore from LTO right away. Repeat that process again for that frame, and there's a really good chance that that frame's going to get there without a problem, because whatever happened to be a transient problem. It's not a problem with what's sitting on tape. It's not a problem, you know, with something that maybe you will never understand, but you know, it's something that just rereading the frame is going to help. All of these components that have these, you know, these fancy saving mechanisms in them, like ECC, they generally have reporting structures. So they have the ability to turn this on into a logging stream, or maybe it already goes to a logging stream. So you can check those from time to time and make sure that, gee, the ECC, it's working perfectly, but guess what? It's reporting bit errors. And if it's reporting bit errors, guess what? At some point in time, it's probably going to graduate to actually causing corruption in your workflow. Again, use high-quality system components. You know, sometimes you can be penny wise and pound foolish. You know, it's the lower quality stuff that's cheaper is generally going to work, but did they cart that off to Lawrence Livermore labs and shoot a neutron beam at it for, you know, 2 weeks and try to discover what's wrong? Probably not. There may be learning some things from that, but probably not. Obviously, more QC through software components is something that it's a great luxury to have if you can spend that time. You know, you can't obviously do everything complete. And then a very simple thing is, again, since you're dealing with file formats over and over and over again, it's probably well worth your time to write software that will go over the file sequences and actually do automatic repair and detection, you know, of those problems. One last thing is, well, there's no reliability built into the DPX format or the EXR format or the camera raw format. So let's think about building that reliability actually into the image format. So what could be done at kind of a high level to do that? Well, you can take an image, a DPX file, and you can FEC, forward error correct that file. And you can actually dial the gauge on how much FEC, how much protection that you want. So you can take that image, you can blow it up by 80%. These are using the same exact techniques that are done by the object store, you know, companies that are you know, that are ensuring your 15 nines or 21 nines of reliability, and then go ahead and store that at rest. When you pull that out of rest, guess what? You can have bit errors even if they happened either at rest or through the network that got them there to you. Even if those bit errors were created, you can go back in and fix that and go back to a bit exact version of that image. So that's really great. Nobody has to touch anything. You can have lower quality equipment throughout your workflow. You can be less concerned about these random writer software bugs and everything, and guess what? You get your perfect image. The obvious bad thing is that that's drawn to scale. So all of a sudden, you've increased your storage by a very, very significant amount. And that's generally not a good thing, and probably nobody's going to jump in and you know, dive into that. So is there an alternative to that? And for these full resolution images that I'm talking about, whether it be camera raw or whether it be you know, these digital intermediate file formats, these things that you're going to stick away for a 100-year archive, well, if you can combine mathematically lossless compression with that forward error correction, you can take that original image and you can shrink the image using the mathematically lossless image compression. And generally, that's going to reduce you, for a good algorithm, down to something about 40% of the size, like a 2 to 2.5, 3, sometimes 5 to 1 type of compression. Well, now you can take that and you can dial way up your gauge to 80%, an 80% coverage with forward error correction. You can put that in a container that has maybe other things associated with that image, and all of a sudden you have the protection for that image. Another byproduct is that when you take that image frame and you do the mathematically lossless compression on it, all of a sudden it is going to be less, you're going to have to worry less about the corruption through TCP, because you don't have that framed segment to combined segment issue that was found in the studies. So is this approach really practical, and if so, why? Well, Moore's law, again, basically has given us tons of computing power. And today we're at the point where you really sort of have to ask the question, is there any reason for images, DI, camera raw, these large images, is there any reason for them to be going around the workflow uncompressed? And you really have to ask that now, but a year from now, 2 years from now, 3 years from now, there's going to be so much compute that it's going to be kind of a strange thing to have that. Really no reason if you can deliver in real time the results to the end workstation. The other thing is that you can actually control the end-to-end workflow now, because what you've done, instead of serial reliability through each stage of the workflow and checking through each stage of the workflow, you can nest the reliability through the outside because you're now going end-to-end. And that changes the calculation for reliability, and that's actually a multiplier that gets you more reliability. So you can dial the level. You can go from the simplest FEC scheme of parity to the most complex FEC scheme, erasure coding or something more complex, and you can guarantee end-to-end that reliability. I mentioned before, now you can consider using a little bit less expensive equipment maybe. Maybe you still want to keep at the high level just to make sure everything flows well. Again, is it practical? Well, so we're combining these things and we have less storage requirements and you're pushing less data around your network. Now, is there a precedence to this? And I think there's a precedence in ST 2022-1 in that that's being applied to sending out video over IP. And basically, they're adding FEC to the row, and they're adding FEC to the column, and if you get to the other side, well, guess what? If you have bit errors in that transmission over IP, then guess what? It can be fixed on the other side, and you don't have to worry about retransmissions. So I think there's a good precedence for that. So in conclusion, end-to-end reliability is really almost impossible to determine. You can determine it maybe at a moment in time, or you can sort of predict it based on what the manufacturers tell you. When you put together a complex system, though, you really don't know. And even though it may look like you have 14 things strung together, when you actually look at all the components it goes in and out of, you're maybe looking at 1,400. Maybe it's 140. I don't know. It's a big number of all the different transitions. Image corruption is very, very expensive. And it's very expensive because it can cause delay. It can cause people to sit around. You can transmit images from the US to India, and it gets there and it's corrupted and you don't know why, and you got to resend it, and that may be hours. It could be days, depending on how big it is. If you want to sort of take a baby step to dip into this, make format-aware correction capability. So you can do that either with the hash schemes, or you can do that with the format-aware that looks at the metadata and does self-correcting. And again, combining the mathematically lossless compression with FEC for these full-resolution images, it's going to give you efficiency, it's going to give you very, very high reliability, and you're going to be able to save money overall with a higher reliability and avoid some of these really costly problems. The other thing to think about when you combine this is if you're sticking something into a 100-year archive, well, guess what? If you stick it into a 100-year archive and you use this approach, that 100-year archive can have bit rot, it can have issues with the data that you get exactly back, but if you have the ability to repair it and get back the exact same MD5 compared, hash compared file, then you're in a really good situation. So that's my proposal. Any questions?
Hi, Aviad from Elanox. Thank you for this presentation. Regarding network or TCP reliability that you were addressing before. So first of all, the first question is, are you talking about a TCP packet reaching the destination, but still, and the TCP stack thinks that the packet is okay, but still there is an embedded error with the transport? Or
exactly,
okay.
yeah. Exactly, and like I said before, that applies to other transport mechanisms that have been done by companies that do proprietary things. You know, they do a good job and, you know, accelerates and all of that other stuff, but, you know, the mileage on it is going to give you some indication of how reliable it is, but each new version has new software and new testing and whatever. There still is vulnerability there.
So I share the same thought, but I think that from statistic point of view, there is a lot of greater chance of just, you know, dropping packets and then reducing the transport or the bit rate because of the nature of the sliding window of TCP itself. And for that, there are new mechanisms like RoCE RDMA over Ethernet and RoCE congestion control to be able to bypass the issue of the sliding window of TCP, reducing the pace and then not providing the workload requirement.
Right. So. Yeah, there's several companies that are in business to do that. I mean, that's what they do, the WAN optimization companies. They do a great job of that. They use up all of the pipe and take out latency and overcome bit errors and problems with TCP. You know, again, the problem is you're going to get corruption when you push this much data down the line, regardless of what's done. But yeah, there's some really good products that solve those problems.
Thank you.
Sure. Anything else? Great.
Thanks, Keith.